Okay, in this lecture, we take a look at the equipotential surfaces associated with a point charge. I have it phrased as an example. Copy it down into your notes as I read it here. Find the electric potential at all points in space due to a point charge Q. For simplicity, we'll assume that the point charge is positive. Okay, now we know ahead of time what the situation has to look like. For example, right here we'll say is our positive test charge, or our positive charge rather, Q. And then of course we have the electric field radially outwards from it. That is like so. Okay, and then recall that the equipotential surfaces are always going to be perpendicular to the field lines. So then therefore the equipotential surfaces are the surfaces of concentric spheres that are centered on the charge. Let me go ahead and draw two of them, like so. Here and here. So these equipotential surfaces are always at a right angle with respect to the field lines. Okay, let's find the electric potential difference between these two spheres. So let's say that this sphere here has a radius of R1, this sphere here has a radius of R2. We're going to go from here to here when calculating the potential difference. So this right here we'll think of as the initial point in the calculation, and this right here as the final point. Okay, now here's the expression that we're going to set up. The integral here on the right-hand side as we go from our initial position to our final position. Okay, now what about the electric field? Well, of course, from Gauss's law or from Coulomb's law, we already know ahead of time what the magnitude of the electric field is. The electric field's magnitude is Q over 4 pi epsilon naught R squared. When I set up this integral, I am, by the way, going to switch variables back to R when I do. I only have to integrate in the radial direction as we go from here to here on the diagram. I don't have to worry about stepping, if you will, along one of the equipotential surfaces, because when I do, there's a 90-degree angle between these two vectors. Cosine of 90 degrees is equal to 0 when evaluating the dot product. So I only have to worry about integrating in the radial direction. Okay, now point B in our calculation is a distance R2 away from the point charge. Point A in the calculation is the distance R1 away from the point charge. And then we have the following integral. Negative integral from R1 to R2 of the electric field in the radial direction. Like so, and now we just do the integration here on the right-hand side. So we have essentially the integral here of negative 1 over R squared. The antiderivative is positive 1 over R. So VR2 minus VR1 equals positive 1 over R, like so, with the constants. And then we evaluate this between R1 and R2 in this basic calculation. Okay, let's go ahead and just plug in our limits. When I do, the potential difference between these two equipotential surfaces is the following. I'm going to go ahead and factor out the constants like so, and then just plug in the limits like this. Okay, now this number, whatever it is, should it be positive or negative? Well, think of it in terms of a positive test charge. A positive test charge always falls from high to low potential. So then therefore, if I placed a positive test charge here, it's basically going to get repelled by this positive charge. So then therefore, a positive test charge here would fall from here to here on the diagram. It would fall from high to low potential. So in other words, as you get further and further away from the point charge, it's like going downhill, if you will, you get to an increasingly lower and lower amount of potential. So the positive test charge would fall from high to low potential. Therefore, if we do final minus initial in our calculation, this number here should be a negative number. So then therefore, it's like 1 over a big number minus 1 over a small number. This then means that the parentheses is negative. Therefore, the potential difference in our calculation, the way that we have set this up, is in fact a negative number, as it should be. Okay, now if we back up to this step here in the calculation, specifically look at the mathematical form of the antiderivative, where should we be such that the potential is equal to 0? Well, you should be at infinity, because for example, if R is equal to infinity, then the 1 over infinity expression here mathematically would give you a value of 0. So then therefore the highest amount of potential is right here as a limit right next to the charge. And then as we move away from the charge, we're increasingly going downhill to zero. Here's how, by the way, we would show that mathematically. Let's go from some random point on the diagram all the way out to infinity. All right, so I'm going to do some erasing here to set this calculation up. Let me just describe it here from scratch. Like so. Okay, so here's our positive charge again. Here's our plus Q. So electric field lines like so. Okay, and then I'm going to go ahead and choose one of the equipotential surfaces. This guy right here, which we'll say is a distance r away from the charge. And then we're going to go from this point in space. I'm just going to refer to it as point P. This is going to be our initial point in the calculation. And then we're going to go all the way out to infinity. That's going to be point B in the calculation. That's going to be our final point. Okay, now here's how we write out this calculation. So VB minus VA, first of all, equals negative integral from A to B of E dot dl. Okay, point B is out at infinity. So we write this as V sub infinity, like so. Then minus the potential at point A, which is this point here in the diagram, just generically referred to as point P. So, equals then the following. Negative integral from r to infinity, that is from here to here, of electric field integrated in the radial direction. The potential at infinity is 0. Once again, it has to do with the 1 over r relationship when I calculate the antiderivative here in just a moment. So 0 minus potential at point P equals then our integral. So integrate negative 1 over r squared is positive 1 over r. So, and then we're integrating from r to infinity here in this calculation. Okay, so let me erase this here from earlier. Okay, so now just negative potential at point P equals then the following. Plug in infinity first and you end up with 0. And then minus with the little r plugged in like so. Cancel out the negative signs and then therefore the potential at point P is described by this expression. So as r increases, you get further and further away from the charge. As r increases, then the potential decreases. It's like going downhill from a peak all the way out to infinity where the potential is equal to 0.